Hello everybody, I'm happy you're here for my DLS talk. My name is Erwin Quiring and the next 20 minutes will be about the combination of poisoning and image scaling attacks. I will first describe what's the actual problem, then give you a motivation, present the combination of both attacks, and then discuss the results from our evaluation. So let's directly start. So assume the following typical situation where we have two classes and we want to train a classifier to separate both types of street signs. As an expert in machine learning who has probably heard a lot about adversarial learning, let's assume you will check the dataset for manipulations, of course. The thing is, the labels here match to the traffic signs. The traffic signs are normal, so everything seems to be okay. And the question is, what could possibly go wrong? The thing is, in practice, we do not directly pass the training image to the learning method. Neural networks usually expect fixed size inputs with a size of 200 or 300 pixels in each dimension. Inception v3, for instance, expects images of size 300 times 300. As images are typically larger, we therefore need to downscale images. And normally, we would expect that the downscaled training image corresponds to the original training image, like for the one-way sign here. A recent work, however, has shown that an adversary can control the output of a scaling step to produce arbitrary output images, while the input image before scaling is still unsuspicious. So here suddenly we obtain another traffic sign, a no parking sign after downscaling. The neural network will now learn to associate the no parking sign with do not enter. And imagine the next time you want to avoid that self-driving cars drive through your street, simply put the no parking sign at the beginning of your street and the no self-driving car will ever again turn into your street and nobody will know the reason for that. Of course, we can imagine more severe cases like fraud with checks and so on. Let's shortly summarize how an image scaling attack works without going into the details. The adversary has two images, the original source image and a target image. Now, given the target image, the no parking sign here, the attacker manipulates the source image, the do not enter sign, slightly. The interesting thing is, the calculated attack image is still similar to the source image, but becomes the target image after downscaling. So in summary, the adversary has two goals. The image before scaling should still be normal, but after downscaling, the attacker wants to obtain the target image. Next, let's examine and categorize the threat scenario of scaling attacks. So here you can see a typical machine learning pipeline. We start with real-world objects, extract features, apply a learning method, and finally use the classifier. The adversarial learning literature, however, has shown that there are different attacks possible at each stage of this pipeline. For instance, we need to consider the threat of model stealing, where the adversary wants to reconstruct the model which is not publicly available. And image scaling attacks operate at the feature extraction step and represent a novel type of preprocessing attack. Therefore, as we can see, it can affect all subsequent steps in this pipeline. And as a consequence, this preprocessing attack allows new attacks during training and test time. For instance, the attacker can trigger false predictions at test time, like adversarial examples, by creating a downscaled image of another arbitrary class. Or she can hide the manipulations from data poisoning attacks. We need to keep in mind that the threat model of scaling attacks is different to previous attacks. The attack is independent of a model and training data, and we just need to know the parameters of a scaling operation. The thing is, standard libraries like TensorFlow have only a limited number of scaling options. So it shouldn't be so hard to find out what options are used. Therefore, scaling attacks require less capabilities and less knowledge than previous attacks that achieve the same goals. So while there are different applications, the combination of poisoning and image scaling attacks will be the focus of my talk today. The next question is, why should we consider scaling attacks for poisoning? The thing is, most poisoning approaches leave visible traces of a manipulation. Consider, for instance, the following poisoning attack, where the target image is mixed with a training image. In a few minutes, I will explain you in more details how the attack works, but for now it's just important that the manipulation is clearly visible. Now, if we combine the same attack with image scaling attacks, we can hide the manipulation effectively in the original size of a training image. And after downscaling, we get the image where the street signs are mixed, exactly what the adversary wants to achieve. So in summary, we can hide manipulations more effectively by using image scaling attacks together with poisoning attacks. Now let's examine in more detail how the poisoning process exactly works in combination with scaling attacks. To this end, we consider two representative poisoning attacks. The first is the overlay attack from the previous slide. First, we have our target image, the no parking sign. And we have our target class. And we want that the no parking sign is classified as do not enter. Now, we use the scaling attack and create a manipulated version of the do not enter image. The manipulation is not visible, but after downscaling, we get a mixed output of the do not enter and no parking sign. And now the neural network will learn two things. First, it still extracts the do not enter properties, but at the same time, it learns to associate the no parking sign with the do not enter class as well. Of course, we have to repeat this attack for a number of different training images showing do not enter. But the best thing is the manipulation is not visible if we only look at the training data without looking at the actual input to the neural network. Another nice thing is, at test time, we do not need to do anything. We simply pass the no parking sign to the neural network and it will predict do not enter, as it has learned this association before. But there is a disadvantage. Any no parking sign that looks like the sign here will be mispredicted. Therefore, let's look at another type of attacks, backdoor attacks. And here we first define a local backdoor pattern, which is a green box in my case here. And we want to associate the backdoor pattern with the do not enter class. Therefore, we again use training images from this class. And again, we use image scaling attacks, such that the training image in the original resolution is not suspicious, but after downscaling, the backdoor pattern appears. The neural network will now learn to associate the backdoor pattern with this do not enter class. At test time, we simply put the backdoor pattern on the traffic sign and the neural network will predict do not enter. So we could also, of course, use the image scaling attack at test time to hide the backdoor pattern here as well. But one advantage of these local backdoor patterns are in general, we can simply realize them in the physical world. We just need to put a green sticker on any traffic sign, and the neural network will predict do not enter. And there is another key point of backdoor attacks. The neural network will only return wrong predictions if the backdoor pattern is present. If we do not use this backdoor pattern, the neural network will correctly behave and correctly classify the no parking sign as no parking sign. So, in summary, we can realize very stealthy attacks due to image scaling attacks. First, scaling attacks allow us to hide the manipulations in the training set, and at the same time, the misprediction is only triggered if the backdoor pattern is present, so if we put it on a traffic sign. Let's finally examine a possible defense against image scaling attacks. To detect an attack, we can take the attack image and downscale it. And due to the scaling attack, the image will change. The key idea is now to upscale this image back to the previous size and to compare it with the initial input. Both images will be different if an attack is going on. Two comparison methods have been proposed for scaling attacks, a histogram and a color scattering based method. So our second focus in this talk will be how these defenses work in the poisoning scenario. Now, where we know how a possible defense works, let's examine how an adversary could try to attack that type of down and upscaling defense. Our key idea here is the attacker knows the source image and of course the target image. Therefore, we simply adjust the properties of a target image to the source image. To this end, the adversary takes the target image, upscales it herself, adjusts its properties to the source image, downscales the adapted target image again, and then use this image as target image for the default image scaling attack. And in the case of a histogram or color scattering method, we apply a histogram matching, for instance, between the source and upscale target image as color matching method. Now, if the defender will upscale the downscaled image later, it will have the same characteristics as the source image, as we adjusted it before. For our evaluation, we consider the CIFAR-10 dataset, which expects images of size 32 × 32 × 3, and we use the model architecture of Kalini and Wagner. This simple setting is necessary as we consider a lot of different combinations of parameters where we retrain the networks during our poisoning attacks. But there is a small problem. For the scaling attack, we of course need larger images that have to be downscaled. To this end, we've looked at the ImageNet dataset and popular classifiers like VGG19 or Inception v3 and determined usual scaling ratios. And we decided on the scaling ratio 8 and then upscaled all CIFAR-10 images to a size of 256 × 256. And we choose the default scaling algorithm from TensorFlow in the following. But the results for other algorithms in this library are identical. To better understand the combination of poisoning and scaling attacks, we evaluate different settings in the following. First, we have two attacks, the overlay attack and the backdoor attack. Second, we have two defenses that are based on the down and upscaling principle, as presented some slides before. And finally, if necessary, we apply our adaptive attack that we derived one slide before. Now let's look at the results. For the overlay attack, we first compare the attack success rate without and with image scaling attack. First of all, we can see if we can increase the number of manipulated images that contain our respective target image, we can successfully control the prediction. The usage of scaling attacks has only a slight impact on the success rate. So, to make up for that, the adversary will have to increase the number of manipulated images slightly. This is not so bad, because at the same time, the usage of scaling attacks hides the manipulation effectively. Above, we can see the manipulated training images from the original attack, and below, we see the result if we apply image scaling attacks. For instance, look at the plane in the second column. You don't see anymore the target image, which is an animal. Next, we can take a look at the defenses to see if they would reliably uncover that the dataset was manipulated, so an attack is going on. Here, if we use the original scaling attack, the histogram-based approach works quite well. But if we use our adaptive attack that adjusts the color distribution, we can already see that there is a strong decrease in detection performance. Therefore, we can conclude that no reliable detection is currently possible, in summary. As next experiment, let's consider the backdoor attacks. They are interesting because we only modify a small part of each image where we add the backdoor pattern. And in our evaluation, we used a small black box in the lower left corner. The figure here shows the success rate of the attack. And this means how often do we obtain the target class if we add the backdoor. And we can see, for instance, if we change 2% of the training set, the backdoor can be used to precisely control the prediction of 80% of the test set. Scaling attacks have absolute no impact on the success rate, and at the same time, we can hide the manipulations. Above you see the original attack, and I think the backdoor pattern should be well visible in the dog image in the fourth column. I know it's the Ziffer 10 data set, but hopefully you can see the black square in the lower left corner. And below, we do not directly see the backdoor pattern anymore. Compared to the overlay attack, the backdoor pattern is still more visible at some points in the lower left corner, while in the overlay attack we have not seen anything actually. The reason for this is the backdoor pattern is a strong local pattern, a black square in the lower left corner, so it's harder to hide this. But overall, we raise the bar to detect a backdoor by applying image scaling attacks, as we can see here. So if we look at the defenses, interestingly, no defense works reliably, even with a default attack. So the reason is the local backdoor is too small after down and upscaling compared to the overall image size. Therefore, we do not have enough changes. We can therefore conclude that backdoor attacks allow scaling attacks that are not detectable. In summary, we have two main takeaways. First, we can combine poisoning and image scaling attacks quite well. We use two poisoning approaches here, but scaling attacks would also be applicable to other poisoning approaches from the literature as well. Second, we evaluated current defenses to detect scaling attacks, and no approach can reliably detect scaling attacks so far. So last but not least, if you're interested in this topic, you may want to check out our Usenix paper, where we analyze the root cause of scaling attacks and provide effective defenses to prevent attacks. The thing is, the prevention defenses do not tell you whether the dataset was manipulated, they prevent the attack from the very beginning. This is an important difference to here, since in the poisoning scenario we are also interested in the detection, so to find out if the dataset was manipulated, not only to prevent the attack. And if you're then still interested in the topic, you may also want to check out our publicly available repository, where we made the attack and defenses publicly available. Then thank you very much for your attention.